Overview of LPC214x microchip units. Welcome to this module on LPC214x microchip units from NXP. This module will overview the LPC214x MCU family and their key features. This TechCast is 24 pages in length and lasts just over 30 minutes. The LPC214x series is the only ARM7 microcontroller family with full USB 2.0 compliance and USB.org certification as of 2008. The full-speed USB 2.0 device supports 32 endpoints with 2 kilobytes of endpoint RAM, 8 kilobytes of RAM usable by the USB DMA, and all data transfer modes. These MCUs allow designers to add USB functionality to almost any end application. In addition to the USB 2.0 full-speed device, these low-power MCUs have from 32 kilobytes to 512 kilobytes of zero-weight state on-chip flash, 8 kilobytes to 40 kilobytes SRAM, 10-bit ADCs, 10-bit DAC, and a low-power real-time clock. These small 10mm by 10mm LQFP64 packaged controllers are loaded with serial communications interfaces including multiple UARTs, I2C, and SPI, as well as 45 fast general-purpose I/O lines. The basic concept on the LPC214x is that each memory area has a natural location in the memory map. This is the address range for which code residing in that area is written. The bulk of each memory space remains permanently fixed in the same location, eliminating the need to have portions of the code designed to run in different address ranges. The MCU generates the appropriate bus cycle abort exception if an access is attempted for an address that is in a reserved or unassigned address region. The figure shows the overall map of the entire address space. Each type of function has its own register. If any are required, and unneeded bits are defined as reserved in order to allow future expansion. Unrelated functions never share the same register addresses. All registers, regardless of size, are on word address boundaries. The MCU includes 4 external interrupt inputs as selectable pin functions. The external interrupt inputs can optionally be used to wake up the processor from power down mode. The MAM block in the LPC214x MCU maximizes the performance of the ARM processor when it is running code in flash memory, but does so using a single flash bank. The memory accelerator module attempts to have the next ARM instruction that will be needed in its latches in time to prevent CPU fetch stalls. The MCU uses one bank of flash memory. It includes 3 128-bit buffers called the prefetch buffer, the branch trail buffer, and the data buffer. The diagram shows a simplified block diagram of the memory accelerator module data paths. The Vectored Interrupt Controller, VIC, takes 32 interrupt request inputs and programmably assigns them into 3 categories: Fast Interrupt Request, FIQ, Vectored IRQ, and Non-Vectored IRQ. The programmable assignment scheme means that priorities of interrupts from the various peripherals can be dynamically assigned and adjusted. FIQ has the highest priority, Vectored IRQs have the middle priority, and non-vectored IRQs have the lowest priority. LPC214 MCUs have 2 32-bit general-purpose I/O ports. A total of 30 input-output and a single output-only pin out of 32 pins are available on port 0. Port 1 has up to 16 pins available for GPIO functions. Port 0 and Port 1 are controlled via 2 groups of 4 registers, including I/O pin, I/O set, I/O DIR, and I/O CLR. All of these registers are located directly on the local bus of the CPU for the fastest possible read and write timing. An additional feature has been added that provides byte addressability of all GPIO registers. A mask register allows treating groups of bits in a single GPIO port separately from other bits on the same port. The UART0 receiver block, U0RX, monitors the serial input line, RxD0, for valid input. The UART0 RX shift register, U0RSR, accepts valid characters via RxD0. After a valid character is assembled in the U0RSR, it is passed to the UART0 RX buffer register, FIFO, to await access by the CPU or host via the generic host interface. The UART0 transmitter block, U0TX, accepts data written by the CPU or host and buffers the data in the UART0TX holding register FIFO, U0THR. The UART0TX shift register, U0TSR, reads the data stored in the U0THR and assembles the data to transmit via the serial output pin TXD0. The UART0 baud rate generator block, U0BRG, generates the timing enables used by the UART0TX block. The U0BRG clock input source is the VPB clock, PCLK. The main clock is divided down per the divisor specified in the U0DLL and U0DLM registers. This divided down clock is a 16 times over sample clock, NBAUD-OUT. The interrupt interface contains registers U0IER and U0IIR. The interrupt interface receives several one-clock wide enables from the U0TX and U0RX blocks. Status information from the U0TX and U0RX is stored in the U0LSR. Control information for the U0TX and U0RX is stored in the U0LCR. The UART1 receiver block, U1RX, monitors the serial input line, RxD1, for valid input. The UART1 RX shift register, U1RSR, accepts valid characters via RxD1. After a valid character is assembled in the U1RSR, it is passed to the UART1 RX buffer register FIFO to await access by the CPU or host via the generic host interface. The UART1 transmitter block, U1TX, accepts data written by the CPU or host and buffers the data in the UART1TX holding register FIFO, U1THR. The UART1 TX shift register, U1TSR, reads the data stored in the U1THR and assembles the data to transmit via the serial output pin TXD1. The UART1 baud rate generator block, U1BRG, generates the timing enables used by the UART1 TX block. The U1BRG clock input source is the VPB block, PCLK. The main clock is divided down per the divisor specified in the U1DLL and U1DLM registers. This divided down clock is a 16 times over sample clock, NBAUD-OUT. The modem interface contains registers U1MCR and U1MSR. This interface is responsible for handshaking between a modem peripheral and the UART1. The interrupt interface contains registers U1IER and U1IIR. The interrupt interface receives several one-clock wide enables from the U1TX and U1RX blocks. Status information from the U1TX and U1RX is stored in the U1LSR. Control information for the U1TX and U1RX is stored in the U1LCR. There are two types of data transfers possible on the I2C bus: data from a master transmitter to a slave receiver, and data from a slave transmitter to a master receiver. The I2C interfaces are byte-oriented and have 4 operating modes: master transmitter mode, master receiver mode, slave transmitter mode, and slave receiver mode. SPI is a full duplex serial interface. It can handle multiple masters and slaves being connected to a given bus. Only a single master and a single slave can communicate on the interface during a given data transfer. During a data transfer, the master always sends 8 to 16 bits of data to the slave, and the slave always sends a byte of data to the master. The SSP is a synchronous serial port SSP controller capable of operation on an SPI, 4-wire SSI, or microwire bus. It can interact with multiple masters and slaves on the bus. Only a single master and a single slave can communicate on the bus during a given data transfer. Data transfers are in principle full duplex, with frames of 4 to 16 bits of data flowing from the master to the slave and from the slave to the master. In practice, it is often the case that only one of these data flows carries meaningful data. The USB is a 4-wire bus that supports communication between a host and a number of peripherals. The host controller allocates the USB bandwidth to attached devices through a token-based protocol. The bus supports hot plugging, unplugging, and dynamic configuration of the devices. All transactions are initiated by the host controller. The device controller enables 12 megabit per second data exchange with a USB host controller. It consists of register interface, serial interface engine, endpoint buffer memory, and DMA controller. The timer counter is designed to count cycles of the peripheral clock, PCLK, or an externally supplied clock, and can optionally generate interrupts or perform other actions at specified timer values based on 4 match registers. It also includes 4 capture inputs to trap the timer value when an input signal transitions, optionally generating an interrupt. The pulse width modulator, or PWM, is based on the standard timer block and inherits all of its features. Although only the PWM function is pinned out on the LPC214x series, the timer is designed to count cycles of the peripheral clock, PCLK, and optionally generate interrupts or perform other actions when specified timer values occur, based on 7 match registers. It also includes 4 capture inputs to save the timer value when an input signal transitions and optionally generate an interrupt when those events occur. The PWM function is in addition to these features and is based on match register events. Basic clocking for the analog to digital converters is provided by the VPB clock. A programmable divider is included in each converter to scale this clock to the 4.5 MHz max clock needed by the successive approximation process. A fully accurate conversion requires 11 of these clocks. This read-write register includes the digital value to be converted to analog and a bit that trades off performance versus power. Bits 5 to 0 are reserved for future, higher resolution digital to analog converters. The real-time clock, RTC, is a set of counters for measuring time when system power is on, and optionally when it is off. It uses little power in power down mode. On the LPC214x, the RTC can be clocked by a separate 32.768 kHz oscillator or by a programmable prescale divider based on the VPB clock. Also, the RTC is powered by its own power supply pin, VBAT, which can be connected to a battery or to the same 3.3 volt supply used by the rest of the device. The purpose of the watchdog is to reset the microcontroller within a reasonable amount of time if it enters an erroneous state. When enabled, the watchdog will generate a system reset if the user program fails to feed or reload the watchdog within a predetermined amount of time. The watchdog consists of a divide by 4 fixed prescaler and a 32-bit counter. The clock is fed to the timer via a prescaler. The timer decrements when clocked. The minimum value from which the counter decrements is 0xFF. Setting a value lower than 0xFF causes 0xFF to be loaded in the counter. Hence, the minimum watchdog interval is TPCLK times 256 times 4, and the maximum watchdog interval is TPCLK times 232 times 4 in multiples of TPCLK times 4. The bootloader controls initial operation after reset and also provides the means to accomplish programming of the flash memory. The flash bootloader code is executed every time the part is powered on or reset. The loader can execute the ISP command handler or the user application code. A ALO level after reset at the PO.14 pin is considered as an external hardware request to start the ISP command handler. The embedded ICE logic provides on-chip debug support. The debugging of the target system requires a host computer running the debugger software and an embedded ICE protocol converter. Embedded ICE protocol converter converts the remote debug protocol commands to the JTAG data needed to access the ARM7 TDMI-S core present on the target system. As the microcontroller has significant amounts of on-chip memories, it is not possible to determine how the processor core is operating simply by observing the external pins. The Embedded Trace Macro Cell, or ETM, provides real-time trace capability for deeply embedded processor cores. It outputs information about processor execution to a trace port. A software debugger allows configuration of the ETM using a JTAG interface and displays the trace information that has been captured in a format that a user can easily understand. Real Monitor is a configurable software module which enables real-time debug. It allows interrupts to be serviced while users debug their foreground applications. It communicates with the host using the DCC, Debug Communications channel, which is present in the embedded ICE logic. Real Monitor provides advantages over the traditional methods for debugging applications in ARM systems.